In this video, we will discuss two-sum binary search tree problem. We'll solve it using two methods. So we have to find out whether there are two elements in a BST that have sum equal to a given target sum. Let's check the first example, 36. So 19 plus 17 is equal to 36. So this should return true because the sum of 19 and 17 is equal to the target sum. For 22, we have 10 and 12. So this should also return true. For 18, we do not have any elements in the BST that have sum equal to 18. So this should return false. And similarly for 13, no two elements have sum 13. So this should also return false. So given any BST and any target sum, we have to find out that whether there are two elements which have sum equal to the target sum. So we'll discuss two methods here. Let's check the first method, which uses a tree traversal and a set. So the logic of the first method is that if the two elements are n1 and n2, which have sum equal to target, so we traverse the tree in the in-order fashion and we keep track of the elements in a set. And if at any point we find out that target minus n2 is already present in a set, that means the two elements are n1 and n2. So we are keeping a track of the previous elements that we have encountered, and if the target sum minus the current element is already present in the set, then we return a true. Let's check it using an example. So we have to find out if two elements have sum 36. So the in-order traversal is left, root, and right. So if you have any doubts on how the in-order traversal works, you can check the video in the top right corner. So the in-order traversal will start from the node 2. Let's create a set. So in the first step of the algorithm, we'll insert node 2 in the set. And we compute a variable diff, which is equal to the target minus the node value. So it is 34. And then we check if 34 is present in the set. 34 is not present, so we continue with the in-order traversal. So next we come across node 7. We insert node 7 in the set and we compute difference of 36 minus 7, which is 29. So 29 is not present in the set. So we continue the inner traversal and we come across node 10. We insert node 10 in the set and we compute the difference. 36 minus 10 is 26. Now 26 is not present in the set. So we come to the next node in the inner traversal, which is 12. We insert 12 in the set and we compute the difference, which is 24. 24 is not present in the set. So we continue the traversal and we come across node 14. We insert node 14 in the set and we compute the difference of 36 minus 14, which is 22. Now 22 is not present in the set. So the next node in the inner traversal is 15. We insert node 15 in the set and we compute the difference, which is 21. So 21 is not present in the set. So we continue with the inner traversal and we come across node 17 and we insert it in the set. So difference of 36 minus 17 is 19. So 19 is not present in the set. So we continue with the traversal and we come across nodes 19. We insert node 19 in the set and we calculate the difference, which is 17. We check if 17 is present in the set. Now node 17 is already present in the set. So when we encounter that the difference is already present in the set, then we return true. So this function will return true. Here we have an extra check that node value is not equal to difference. This check is because let's say we have to find node 34. So 34 is not present in the tree, but 17 plus 17 is 34. So to avoid this, that an element is not counted twice, we check here that node value is not equal to the difference. So the difference should be present in the set and the node value should not equal to the difference. Then we return true. So this method uses a set to store the previous values that we have encountered, and if the target minus the current value is already present in the set, then we return it true because the two elements are present. If we look at the time complexity of this method, this is order of n, and the space complexity is also order of n because we are using a set to store the elements. Now we have another method also which is a slightly more efficient in terms of space complexity. Let's have a look at the second method. Now the second method uses a technique which is known as two-pointer technique. So two-pointer technique is mostly used when the data is sorted. Let's say the sorted array is given and you have to find out if two elements are present in this array which have sum equal to 36. Now in two-pointer technique, we keep two pointers. One is pointing to the first index of the array and the other pointer is pointing at the last index of the array. So let's name them low and high. So at each step, we compute the sum of low and high. So now low plus high is 22. This is less than 36. So because the array is sorted, if we have to reach sum 36, then we have to increment the low pointer to the next index because it is in increasing order. So now low will point to 7. We again find out the sum. So it is 7 plus 20, which is 27. It is again less than 36. So now we again increment the low pointer. It is pointing to 10. So it is 20 plus 10, which is 30. So it is again less than 36. So we again increment low. It is now pointing to 12. So now it will be 32, which is again less than 36. We again increment low. So now it is 14. So it is 34, which is again less than 36. We again increment low. So it is 15. So the sum is 35, which is again less than 36. Now we again increment low. We reach 17. 17 plus 20 is 37. So which is now greater than 36. So now to reach 36, we have to decrease the sum. To decrease the sum, we decrement the high pointer. So the high is now pointing to 19. So 17 plus 19 is 36. So which is equal to the target sum. So we return true. Let's check the second example, which is 18. So high is pointing to the last index, which is 20, and low is pointing to the first index, which is 2. We compute 2 plus 20, so it is 22, which is greater than 18. So now to reach 18, we have to decrement the high pointer. So we decrement high, it comes to 19. So 19 plus 2 is 21, which is still greater than 18. So we again decrement the high pointer. We reach 17. So low plus high is 19, which is again greater than 18. So we have to again decrement the high pointer. So now it is 17, which is less than 18. So to reach 18 now, we have to increment the low pointer. So it is 7 plus 15, which is 22. So it is greater than 18. To reach 18, we have to decrement the high pointer. So we decrement high to 14. So 14 plus 7 is 21. It is still greater than 18. So we again decrement the high pointer. So now we are at 12 plus 7, which is 19. We are again greater than 18. So we again decrement the high pointer. We reach 10. So 10 plus 7 is 17, which is less than 18. But now if we increment the low, it will be equal to high. So now we'll stop it and we'll return a false. So there are no two elements present in the array which have sum equal to the 18. So now this two pointer technique works for the sorted array. But in BST we have a property that the left nodes are smaller and the right nodes are larger. So we can use the same two pointer technique in this BST to find out if there are two elements present which have the sum equal to the target sum. So let's see an adaptation of the two pointer technique for the BST. So in the first step, we create two stacks, stack 1 and stack 2. We push all the left nodes of the root in stack 1. So the left nodes are 15, 7 and 2. So we'll push all these in stack 1. And in the next step, we push all the right nodes of root in stack 2. The right nodes of root are 15 and 20. So we'll push both 15 and 20 in the stack. Then we keep two pointers, low and high. Low will point to the top of stack 1, which is 2. So low is pointing to 2 and high is pointing to 20. So you can see here that low is pointing to the smallest element of the BST and high is pointing to the highest element of the BST. So it is like a sorted array where low is the first index and high is the last index of the array. Then we have a while loop which we have to run while low value is less than the high value. So here 2 is less than 20, so we'll come inside and we compute the sum. So 2 plus 20 is 22. We check if sum is less than target. So 22 is less than 36. This is true. So we push all left nodes of low right in st1. So right of 2 is null, so we do not push anything in the stack. So low becomes equal to top of stack 1, which is 2, and then we pop from stack 1. So we remove element 2 from the stack. In the next iteration, we check if low, which is 2, is less than high, which is 20. We compute the sum, it is 22. We check if 22 is less than 36. We push all the left nodes of right of 2, which is null. So there are no nodes. Low becomes equal to top of stack 1. So now low will point to 7. And then we pop from the stack 1. So we remove 7. So here we saw that when sum, which is 2 plus 20, is less than 36, so we have to increment the low index. So we incremented the low from 2 to 7. So basically this if statement is incrementing low, and the next if statement, when the sum is greater, we decrement high. Let's check the next iteration. So now low is 7 and high is 20. We compute the sum, it is 27. We check if 27 is less than 36. Now we push all the left nodes of right of 7 in the stack 1. So right of 7 is 12. So we push 12 and 10 in the stack 1. And then low becomes equal to top of stack 1, which is 10. And then we pop from the stack 1. So we remove 10 from the stack. In the next iteration, we check if low, which is 10, is less than 20. We compute the sum, it is 30. We check if 30 is less than 36. Then we push all the left nodes of right of 10. This is null. We set low to the top of stack 1. So low becomes equal to 12. And then we pop from stack 1. So we remove 12. In the next iteration, we check if 12 is less than 20. We compute the sum, which is 32. 32 is less than 36. So we push the left nodes of right of 12 in the stack 1. So the right of 12 is 14. So we push 14 in the stack. Low becomes equal to top of stack 1. So low becomes 14. And then we pop from the stack. So we remove 14. In the next iteration, we check if 14 is less than 20. We compute the sum, which is 34. 34 is less than 36. We push all the left nodes of right of 14, which is null. And low becomes equal to top of stack 1. So low becomes equal to 15. And then we pop from the stack 1. So the stack 1 is now empty. In the next iteration, we check if 15 is less than 20. We compute the sum, which is 35. 35 is less than 36. Now we push all the left nodes of right of 15. So right of 15 is 20. So we push all the left nodes of 20 in the stack. So we push 20 and 17 in the stack. Low becomes equal to top of stack 1, which is 17. And then we pop from the stack. So we remove 17. In the next step, we check if 17 is less than 20. We compute the sum, which is 37. So now 37 is not less than 36. So we come in the next if and we push all the right nodes of left of 17. So in stack 2, we push 17 and 19. High then becomes equal to top of stack 2. So high is 19. And then we pop from the stack. So we remove 19. In the next iteration, we check if low is less than high. So low is 17, which is less than high. We compute the sum, which is 36. So now we come in this if statement when sum is equal to target. So we return true. This means that two elements low and high, which are 17 and 19, are present in the tree which have sum equal to target, which is 36. So as we saw in this method, we keep two pointers. One is pointing to the smallest element and the other pointer is pointing to the largest element of the BST. So if the sum is greater than target, we decrement high, and the sum is less than target, we increment low. And if at any point the sum is equal to target, we return a true. So we keep doing this as long as low is less than high. If low becomes equal to or greater than high, then we break and we return a false. Now the time complexity of this method is also order of n, but this is a slightly more efficient in terms of space. So here the average space complexity is order of log n, which is the height of the BST. So once you've understood both these methods, let's have a look at the implementation. All the source code that I'll be showing is available in my GitHub repository, link of which is available here and as well as in the description. Now let's have a look at the code. So in the main function, I've created the BST, the root node is 15, the left of root is 7. In this manner, I've created all the nodes of the BST. Then I have this function find target in which I'm passing the root and the target sum. So I'm passing all the target values at 36, 12, 18 and 13 and calling this function find target. In this function find target, I create two stacks of type tree node. I push all the left nodes in stack 1 and I push all the right nodes in stack 2. In this function push left nodes, I simply keep going on the left and I push all the nodes in the stack. And in the function push right nodes, I keep going to the right and I push the nodes in the stack. Then I keep two pointers low and high. Low is pointing to the top of the stack 1 and high is pointing to the top of the stack 2. Then I have this while loop which I run till low is less than the high. I compute the sum of low and high, and if the sum is less than the target sum, I increase the low. To increase the low, I push all the left nodes of right of low in the stack. So now low will point to the stack top and then I pop from the stack. If the sum is greater, I decrease the high. So I push all the left nodes of the high in the stack. And now high will be pointing to the stack to top and I pop from the stack. If the sum is equal to the target, I return it true. If low value is equal to the high or it exceeds, then I break from the loop and I return a false. Let's have a look at the output of this program. So for 36 and 22, it returns true because 19 and 17 have sum equal to 36 and 20 and 12 have sum equal to 32. But no elements are present which have sum equal to 18 and 13, so I return a false. So that was all for this video. If you have any doubts or suggestions, please leave in the comment section below. If you like my content, please do like, share and subscribe to my channel. It really motivates me to make more such content. And until next time, this is Sandeep Thapar signing off.